Okay, welcome to our 2.8 examples video. Hopefully at this point you guys have already started on the homework, and watching through this video can help clarify a few things as well as help you get through spots where you're stuck. But in this video we're actually going to start with number 9. And number 9 is actually one of the last ones in your homework, and the reason why is take a look at what it's actually asking for. It's asking for the second derivative. So of course we'll go through how to actually find the second derivative, but in order to find the second derivative, we need to first find the first derivative. And for that reason, this example is a good review of everything that we learned in the concepts video. So this will be a great example of just what does it look like to differentiate implicitly. What does implicit differentiation look like? So we have the equation 3y squared minus xy plus 5x squared equals 6. And this is a cool example because if you try and solve for y, it's impossible. It's impossible to solve for y, so implicit differentiation is our only option. If we remember back from the concepts video, one of the big ideas with implicit differentiation is we're going to go ahead and take the derivative right now. Take the derivative in terms of what? Well, if I come up here and look, I have dx in the bottom, so that means I'm taking the derivative in terms of x. And remember, with equality, whatever you do to one side, you have to do to the other side. So I'm taking the derivative of both sides of this equation. So if I look at each side, well, this first side is just the derivative of the constant 6. The left side, I can use my sum and difference rules of derivatives. So I get the derivative in terms of x of 3y squared minus the derivative in terms of xy plus the derivative in terms of x of 5x squared. So now we can look at smaller pieces and what their derivatives are each going to be. And let's go right to left, because I think right to left, we're going to go from less complicated to more complicated. So let's start with this. What's my derivative of a constant 6? We already know that. The derivative of a constant is just 0. Okay, next piece. The derivative of 5x squared. 5x squared is a function in terms of x, and we're taking the derivative in terms of x. So with this term, because it's already in terms of x, there's nothing complicated about this. I can use my normal derivative rules. The derivative of 5x squared is 10x, just using the power rule. Okay, but now we get to a complicated piece. So now let's look at the derivative in terms of x of xy. Well, an important thing to remember is if you have xy next to each other, that's technically multiplication. So you have x times y. And remember, what are we assuming about y? We know that y depends on x. That's what this equation tells me, is that y depends on x. So that means this is a function of x. But so is x. Both of those are functions. And what happens when we have two functions multiplied by each other and we take the derivative? We have to use product rule. So for this function, we have to use product rule. So for this first function, we're going to go ahead and say the first function is just x, and the second function is this y. Well, the derivative of the first function is easy. It's just 1. What about the derivative of the second function? Well, this is where we can use a little bit of that implicit differentiation to say, okay, well, normally I'm taking the derivative of x, but if I want to switch it to taking the derivative of y, all I have to do is just add in a dy over dx. And then I can take the derivative of y in terms of y. So what's the derivative of y in terms of y? Just 1. And we get dy over dx, or y prime. And that makes sense, right? What's the derivative of y? It's just y prime. And so if you wanted to skip to that point, that's totally fine. So there's my two derivatives. And now I can cross multiply and add them together. So the derivative of this middle portion, I'm going to keep that minus outside the parentheses because there's addition involved with the product rule. I get x times y prime, or dy over dx, plus y times 1. And that's the middle term. Last, we have the derivative of this function 3y squared. But remember, we're taking the derivative in terms of x of a function that's in terms of y. So how do we deal with that? Remember, we just switched d over dx to dy over dx times d over dy. And now we can take the derivative of 3y squared in terms of y. And I can take my derivative like normal. And I'm left with this dy over dx. Or remember, how else could we write that? We could just write that as y prime. So y prime, what's the derivative of 3y squared? I get 6y. And then I'll distribute this negative to both terms, and I'm left with that. So this is a good review of how implicit differentiation works. At this point, remember, what are we solving for with implicit differentiation? We're solving for dy over dx, or y prime, right? That's what we're solving for. So what I want to do from now is everything that has a y prime, I'm going to keep on one side, and everything that doesn't have a y prime, like this y and this 10x, I'm going to move to the other side. Now that every term on the left side has a y prime in it, I can factor that out, and then I can divide by that extra factor. And I'm left with y prime is equal to y minus 10x over 6y minus x. Remember, y prime is just another way to write dy over dx. So I found my derivative. My derivative is this function that's in terms of both y and x, but it's y minus 10x over 6y minus x. So at this point, if your function or if your problem gave you a coordinate point, you could plug that coordinate point in to find what the slope is at that specific point. Right? That's what the derivative tells me. It tells me what the slope is at that point. But this problem's a little different. This problem wants me to find, okay, now what's the second derivative? So we're actually only halfway done with this problem because now we found the first derivative and we now need to find the second derivative. Well, how do you find the second derivative? You take the derivative of the derivative, right? I'm going to take the derivative of this in terms of x. And this is going to require a little bit more implicit differentiation. So d squared y over dx squared is going to equal, well, tell me, if I want to take the derivative of something like this, what is that going to require? If I'm taking the derivative of a function over another function, that requires quotient rule. So I've got to come over here and say, okay, well, my numerator function is y minus 10x, and my denominator function is 6y minus x. What's the derivative of my numerator? This requires a little bit of implicit differentiation just with this first term. What's the derivative of y? It's y prime. Minus, what's the derivative of 10x in terms of x? Just 10. So I get y prime minus 10. What's the derivative of the denominator? Well, very similarly, 6y, when I take the derivative of that, I take the derivative like normal, which would give me 6, but then I multiply it by y prime. So I get 6y prime minus derivative of x is just 1. And now I put it together using the quotient rule. And I get denominator multiplied by the derivative of the numerator, so y prime minus 10, minus the other pairing, so numerator y minus 10x times the derivative of the denominator, so 6y prime minus 1, all over the denominator squared. Whew. So there's my second derivative. So all I've done so far is just use the quotient rule with a little bit of implicit differentiation. But here's my problem is we were okay with the first derivative being in terms of both y and x. That's fine. Notice what this second derivative is in terms of. It's in terms of y, x, and y prime. But what is y prime again? Y prime is really just that first derivative, dy over dx. And turns out we know what this first derivative is equal to. That's what this is right here. The first derivative is equal to y minus 10x over 6y minus x. So I can come back here and plug that in for dy over dx, or y prime. There's one y prime that I had to plug it in for, minus y minus 10x times, and then here's the other one, 6 times y minus 10x over 6y minus x, all over 6y minus x squared. Now, even though this is really, really complicated and convoluted, this second derivative is now completely in terms of only x and y. And so, I can be done. There is simplifying I could do. If I wanted to go through, find some common denominators, combine my fractions, there's a lot of simplifying I could do, but it's not worth the time and effort just go ahead and plug it into Pearson like this, and it'll give you credit. But this is my second derivative because I found my first derivative, then used the quotient rule to get the second derivative, and wherever I saw a y prime or a dy over dx, I plugged in that first derivative. And that takes care of that one. Okay, let's look at our next problem. We're going to just go back one to problem number 8. So this deals with a ladder leaning against a vertical wall, but that lower end is being moved away from the wall. I don't know if it's slipping or what. It's moving at a rate of 5 feet per second. And this question is asking, if this is moving this way, how fast is the top of the ladder moving down the wall? Well, why is this implicit differentiation? Because this is a great example of related rates. Everything is changing in terms of time. The ladder is moving over time, and so each of these distances is changing as time passes. It all depends on time. So we have x, we have y, and we have the length of the ladder. What shape is this creating? It's creating a right triangle. So do we have an equation that relates the size of a right triangle? We do. It's Pythagorean theorem. So x squared plus y squared is equal to 10 squared. That's what Pythagorean theorem tells us, right? That the two legs of your right triangle, the square of their sides add up to be the square of the hypotenuse. So x squared plus y squared is equal to 10 squared. Well, let's take a look at some of the things that we know. First of all, we already know the ladder's 10 feet long, and I've already used that. That gets put in right here. What else do we know? We know that the lower end is being moved away at a rate of 5 feet per second. The lower end is dealing with x, right? X represents the lower end of the ladder. We can see that right here. But 5 feet per second is a rate. It's the rate at which it's moving. So how would I express this mathematically? This is dx over dt. It's how x is changing over time. So we know that dx over x, or dx over dt, or I could also write this as x prime, because it's the derivative of x in terms of t, is changing at a rate of 5 feet per second. So that's one piece of information it gives me. It gives me the rate at which x is changing. It also tells me this, when the lower end is 6 feet away from the wall. What is that telling me? Is that a rate? No, that's an actual distance. So that's telling me that we're looking at the point when x is equal to 6. Notice how that's not a derivative. That's just a distance. It's not a rate, it's just a distance. It's just an x value. Now, what are we searching for? Let's look at where the question is. How fast is the height of the top changing? So what are they asking for? Are they asking for a distance, or are they asking for a rate? Since it's asking how fast, this is asking for a rate. And since it's talking about how the top is changing, we're looking at my y distance. So what is it asking for? It's asking for dy over dt. Remember, I could also notate that y prime. Which means, what am I going to do to this Pythagorean theorem equation? I'm going to take the derivative of everything in terms of t. That's what makes this related rates, is everything depends on time, so you're taking the derivative in terms of time. So, d over dt of x squared, plus using my sum and difference rule of derivatives, I can separate this into two different derivatives, and then I'm also taking the derivative of my constant 100. We know what happens to the right side, it just becomes 0. But what about each of these derivatives on the left side? Since I'm taking the derivative in terms of time, I'm going to use implicit differentiation for both of these pieces. I'm going to take the derivative like normal, but then multiply by dx over dt, or x prime. Same thing with the other piece. You'll take the derivative like normal, but then multiply by dy over dt, or y prime. Okay, very nice. Now what? Well, this is where we go to what values do we actually know? We know what x is because it specifies when we're looking. We're looking when x is equal to 6. We know what dx over dt is. We know the rate at which x is changing, or the lower end. We know that's changing at a rate of 5 feet per second. What about in the second term? Well, first of all, dy over dt is my question mark. That's what I'm solving for. But in order to be able to solve for that, I do need to know what y is. Can I figure out what y is? I actually can if I come back up here and use my original Pythagorean theorem. So come on down here and take a look what happens. Pythagorean's theorem tells me, x squared plus y squared is equal, in our case, 100. What was x again? X was 6, so I can plug 6 in for x, and now I can solve for y. And I get positive 8. Technically positive or negative 8, but we of course know this, we're working with positive values since we're talking about a ladder leaning against a wall. So what does that tell me? That tells me if the ladder starts 6 feet away from the wall, then it has to start 8 feet high on the wall. We know the corresponding y value, and I can use that y value in my equation. I can plug 8 in for y. Perfect, and now we're ready to solve this. So 2 times 6 times 5 plus 2 times 8 times, I could put a question mark or I could just leave it as dy over dt, is equal to 0. 2 times 6 times 5 gives me 60, plus 2 times 8 is 16 times dy over dt. I'll subtract 60 on both sides, then divide by 16. And I get negative 15 over 4. Interesting. So I wasn't okay with y being negative, but is it okay if the derivative's negative? Absolutely, because what does that mean? That just means the ladder is moving down. Instead of moving up, it's moving down. So the ladder is moving down at a rate of 15 over 4 feet per second. Or if I put that as a decimal, it's just negative 3.75. So with related rates, everything depends on time, so you're taking the derivative in terms of time of everything. Okay, good luck with the rest of the problems on your homework. Reach out if you have any questions, and I'll see you when we move on to the Chapter 3 videos. Good luck.